Hi, this is Mr. Mack. We're going to talk during this session about reciprocal functions. Now, basically, reciprocal function, or the basic reciprocal function is f of x is equal to 1 over x. Now, there's a number of things that we need to discuss about this reciprocal function. The first thing would be, what is the domain? Now, at this particular point, when anybody asks what is the domain, what I want you to think is, what are the values that x can't be? Well, obviously here, x can't be 0 because that would make the denominator of this function 0. And any other value, though, would work. So the domain is all reals except except 0. A lot of times for the domain, people just write x is not equal to 0, which would be everything on the number line except the point 0. Now the next question is, what is the range? And this one is more intriguing. See, now, if you were to just look at some values, x, f of x, misguided look might say, well, we can't use 0 because x can't be 0, so if we try 1, 1 over 1 is 1. If we try 2, we get 1/2. If we try 3, we get 1/3. If we try 4, we get 1/4, and so on like that. If we try 10, we get 1/10, and so on like that. So as x would get larger and larger, our numbers would be getting closer and closer to 0. But what about 2 down here? Is there any way we could get 2 or even 10 down in the range part? Well, the truth is we can, but those are all found in a very small interval. In other words, if I were to put 1/2 in for x, and let's take a look at that. If f of 1/2 is really 1 over x, which is 1/2. Now, you've learned by now, I think, that when you are dividing by a fraction, that what you do is you flip the second fraction and multiply, so that'd be 1 times 2 over 1, or 2. So notice that the x value that would give you 10 would be 1/10. Now, if you wanted to get, like, say, 100, or let's say even 1,000, if your x value is 1 over 1,000, then 1 over 1/1,000 would be 1,000. So we can get any positive number, no matter how large, by just putting its reciprocal in for the input value. Now, that means okay, I was interrupted there for a minute. I'm back. So actually, we could get any number, no matter how large, by just putting its reciprocal in. Now, if we investigate the negative numbers, we get, once again, x, f of x. If we put in -1, we would get -1. -2, we get -1/2. -3, we get -1/3. So notice, as x goes towards larger negative numbers, like -100, -1,000, and so forth, we're getting numbers that are getting closer and closer to 0, but from the negative side. And so the question is, how about -10 or -100 or -1,000? Well, once again, if we put in -1/2, we would get -2. -1 over 100, we would get -100 out. So as you can see, we could get any number, no matter how negative, large in the negative sense, by just putting its reciprocal in. So the only number that we can't get for the range would be the number that doesn't have a reciprocal, and that would be 0 itself. So for the range, we get the same set that we have for the domain, all real numbers except 0. So for the range, y is not going to be equal to 0, but it could be anything else. Now, the strange thing about this is that this function, if you look at its graph, this function, when x is 1, y is 1, 2, we have 1/2, 3, we have 1/3, and so forth like this. All the way out to infinity, from 1 out to infinity, we're between 1 and 0 for x. And at -1, we get -1. At -2, we get -1/2. So all the way out from -1 to negative infinity, our y values are between -1 and 0. The place where we get all of the other values for the function are between -1 and 1. In other words, the function just kind of curves up towards the y-axis and heads towards infinity on the positive side, and it curves down from the y-axis and heads towards negative infinity on the left side of the y-axis. Now, we call this behavior the behavior where a graph approaches but curves away from. In other words, it's not going to actually touch the y-axis, but it's going to get closer and closer and closer. We call this asymptotic behavior. In other words, the y-axis is an asymptote, A-S-Y-M-P-T-O-T-E. This is a line that the graph gets closer and closer to, but never touches. Closer and closer to, but never touches. So in this case, in other words, in f of x is equal to 1 over x, the y-axis is an asymptote. Now, notice, I'm sure that you've noticed, that the y-axis is a vertical line. So since the y-axis is an asymptote, a line that the graph gets closer and closer to and never touches, and it's vertical, we call it a vertical asymptote. Now, also, if you'll notice, if we go back to the x values and the y values, as x is getting larger and larger, or as it's getting larger and larger negatively, the y values are getting closer and closer to 0. Now, if you look at the graph, notice here that as the graph goes farther and farther out, it gets very, very close to the x-axis here, and also it'll get very, very close to the x-axis over here. But no matter how big this number is, 1 billion, 1 over a billion, although it's really close to 0, is still not 0. This line will never, this graph will never touch the x-axis either. So the x-axis is also an asymptote of this graph. And if you look at the graph, the behavior is that it moves toward but curves away slightly from these lines that it's getting closer and closer to. It never turns. It never turns and goes farther away from it, but there is this slight curve that keeps it from actually running into the line. This is not the way it behaves. But it gets closer and closer to the x-axis, but it never actually touches it. We call that asymptotic behavior. Now, this graph is a graph that has a name. Any graph that, I'll use asymptote as a verb, although that's probably horrible. Any graph that asymptotes in both directions, like this, is called a hyperbola. Okay. So we have a new parent function here, and the parent function is the reciprocal function, or the hyperbola. Now, because it's a parent function, that means that we are going to expect you to be able to transform it, or to do transformations with it. So let's take a look at some of these. Remember, let's just go to full page here. Remember, when we have y, or f of x, is equal to 1 over x, if we do something to the graph before the graph is, if we do something to x before we perform the function, then that's a horizontal effect. So if we were to, say, subtract h from x before we reciprocate it, this would be a horizontal shift. In other words, f of x is equal to 1 over x minus h would shift, and let's imagine for the moment that h is positive. This would shift this graph h units to the right. In other words, the vertical asymptote of the graph, which is what is really kind of the middle of the graph, would be shifted h units to the right. Now, if we had x plus h, where h was a positive number, it would shift it h units to the left. Now, remember also the x-axis is the horizontal asymptote. It's kind of the center of the graph as well. If we put plus k, then this would shift the graph. See, that's after the function has been performed. This would shift the graph up or down, and what would be the central feature there again would be the horizontal asymptote, which was at the moment the x-axis, but it would become another line. And then if we do a vertical stretch, we would multiply by a, and so that would end up here. So a would be our vertical stretch on the graph. Now, this is fundamentally the kind of transformations that we would expect, and we're going to expect you to be able to graph functions, reciprocal functions, when they look in this particular form. And what you need to remember is that h is the place on the x-axis where the vertical asymptote is. K is the place on the y-axis where the horizontal asymptote is. And then usually the easiest thing to do is to put in the vertical and horizontal axis asymptotes as dotted lines, and then pick a point, maybe to the left of the horizontal asymptote, the vertical asymptote, and to the right of the vertical asymptote. Find out what f of x is in those cases, plot those points, and then just draw the graph asymptoting to the two asymptotes, if to asymptote can be considered a verb. Now, I'm going to be doing several problems in the solutions video, but that pretty well covers reciprocal functions. So we're done.